Welcome. In this section, we'll try to develop a mathematical function which has a constant magnitude for all the frequencies, but it changes the phase depending on the frequency of the signal. So the attempt here is to try to discover such a function through a Python programming. So let's get started. I have downloaded NumPy and Matplotlib, and let me define the parameter of this math function. So firstly, since we have to pass all the frequencies through this function, so let me create an array of frequencies starting from, let's say, 1 hertz going up to 10 kilohertz. Let's say in we need 1000 such frequencies, and let's say we have a variable R standing for resistor, and let's say it's a 1 kilo ohm resistor, and we have a capacitor which is, let's say, 1 micro farad. So now omega, which is the angular frequency in radians per second, is defined as 2 pi f, so 2 into pi into the frequency array that we created. So now we have our frequencies in radians per second, and let's attempt a function. Don't ask me the reason why we are considering it, it will become evidently clear later. But let's say we create a function whose numerator is like this. It's a complex number, let's say 1 minus, so in Python complex numbers are represented like this, 1j. The imaginary part is omega multiplied by r multiplied by c. So let's say this is our numerator. Don't ask me the reason why I have chosen this, it will become clear later. And let's see, we have a denominator of a function which is just a sign change here, nothing else, everything remains the same. And let's call this function as h of w. So this function now is nothing but numerator divided by denominator. So it's basically a complex number function, and this function, let's see what it looks like. So so as you can see, this is these are all complex numbers, and they are varying in magnitude. They are different numbers here, 1000 of them. So I'll do one thing, I'll calculate the magnitude and phases of this function. So basically what we have done is we have passed all these frequencies through this variable into this function, and we are now trying to see the magnitude and phases. So in to calculate the magnitude, let's define a variable magnitude, and in NumPy, the magnitude of a complex number is calculated like this. So it's pretty simple. And the phase of complex number is calculated like this. So we pass on this complex function, and we want the output in degrees. So let me just say degree equals true. So this way we are able to create the magnitude and phases. Let's just have a look at the magnitude. Something very surprising happens here. There's a constant magnitude of 1 for all the frequencies. Now that's quite surprising. And what about the phase? So let's see. Oh, so we have phases starting from minus 0 degree, and it is going up to almost quite a bit of numbers here, almost 180 degrees, minus 180 degrees. So that's quite a interesting thing. So let's continue our journey further. So let's say if I know that my phase is varying from 0 degree to minus 180 degree, and I'm interested in finding out at which frequency my phase becomes minus 90 degree. So how do I go about doing it? Is like this. So my target phase, for example, is minus 90. So I have to find out at what index this minus 90 degrees is happening in the array, and basically I'm trying to find the address of the data point where the phase is minus 90 degree. So basically what I'm trying to do is I'm trying to go through all my phases, and then I'm looking for my target phase. So if the moment I find minus 90 degree, this whole number will become 0, phase minus target phase. Let me take an absolute values to get rid of the sign. So this number, if wherever phase is equal to target phase, this number will become 0. And basically I am looking for the address where this is happening, or the index where this is happening. So that in Python is found out using this argument function. So now I know where this phase is becoming minus 90 degree. So the closest frequency where this phase is becoming minus 90 degree is basically, I will just go through my complete frequency array and I pass on this address or the index. So this should give me at what frequency my phase is turning to minus 90 degree. And let me just print it out then. Frequency at minus 90 degree and minus 90 degree phase shift, and this will be closest frequency, and I just want 1 decimal point, and this will be in hertz. So let me just print this. Amazing. So we get this number. Frequency at minus 90 degree phase shift is 161.1 hertz. Let me just increase the resolution. Let me see, I want in my frequency axis, I want 10,000 number so that I get a good resolution. Yeah, so it is 159 hertz. This is because I've increased the resolution in the frequency axis. So that's a very good conclusion. Now what do we do is, so this is by going through this frequency array and checking phases at each and every frequency and then matching wherever the phase changed to minus 90 degree, I picked up that frequency. That was a very crude way of doing it. Is there can we find a mathematical formula to get it? Let's see. Let's define a variable called frequency 90, and I'll use a formula. Don't bother where this formula has come from, but let's see what this formula does. So 2 into n, 2 into pi into r into c, and let's see what is the frequency at this point. So let me just print this out. So my frequency 90 is nothing but frequency 90, and I want only 1 decimal point, and this will be in hertz. So let me just print this. Interesting. So this formula is also leading us to the same frequency, which is almost matching with the empirical method that we used earlier, which means this formula takes us to this formula, which is 1 divided by 2 pi RC, is a formula which takes us to that frequency which undergoes minus 90 degree phase shift. Alright, so I'm now going to do some plottings. I have already written the code for that. So basically what I'm doing here is I am plotting on my x-axis the complete frequencies that have passed through this function, and then I am on the y-axis I'm going to plot the magnitude. Similarly, I'm going to plot the phases, and what I'm doing here is that I have taken my complete frequency axis on x-axis, and then on my y-axis I have phases, and rest other things are only to embellish the plots. So let me run this entire code now. Amazing. So let's see the magnitude plot. So on the x-axis we have frequency, and it's going from 0 hertz to 10 kilohertz, and on the y-axis we have the magnitude, and it should not be no surprise that the magnitude is 1 all throughout, irrespective of what frequency you choose, which means it is allowing all the frequencies to pass through, and that's a typical characteristic of all pass filter. What about phase? So here is phase. Again, we have frequency axis on x-axis, and on y-axis we have phases, and we are seeing that the phase changes from 0 degree to minus 180 degree, and this is a very asymptotically this is converging to minus 180. And then we have done some plotting to see where my phase becomes minus 90. So at this point, and it intersects the curve at this point, this blue curve, and frequency there is 159 hertz, and this we also checked here. So the takeaway here is that the magnitude, the function that we have defined, is a very beautiful one in the sense that it allows all frequencies to pass. It doesn't attenuate or amplify any other frequency. But when it comes to phases, it is manipulating, it is changing those phases from 0 degree to minus 180 degree, depending on what frequency you are at. For example, if you're at 1 hertz, you are almost having no phase shift. But when you come to 159 hertz, you have minus 90 degree phase shift. And if you keep coming down and down and this frequency keeps increasing, you are basically converging towards minus 80 degree phase shift. So we have found a beautiful function which is doing this job, which is this one. And we have discovered another formula, which is this one, which is telling us the frequency at which minus 90 degree phase shift happens. Now, how to implement this formula using electronic components, this is what we are going to do in the next section. I hope you enjoyed. Let's see in the next section. In the last section, we saw this magical function, this one, and we analyze the properties of this function, and we realize that the magnitude of this function is always 1, and the phase changes as per the frequency. So now we'll continue our investigation into this function, and basically we would like this function to be implemented by an electronic circuit, and here we have an op-amp circuit here, and let's see what kind of function this op-amp circuit generates. So it's pretty simple circuit. On the inverting input, I have 2 resistors connected. One is this input R1 here, and then there's another one in the feedback path R1. Both of them are same value, so the output gets fed back to the input. And on the positive terminal, I have resistor R2 connected. This R2 is different from the R1, and we have this capacitor connected to this terminal, positive terminal, which in turn is grounded here, and our input is connected to both these positive and negative terminals. And we need to analyze this circuit and come out with its transfer function. So we'll use the method of superposition, and we'll analyze the functioning of this circuit. So I'll split the circuit into 2 parts for the analysis purposes. In the first part, I'm going to manipulate this input. So I will keep, like, as you can see, I have grounded this input, the negative terminal input, and I have given V in only to the positive. This will generate some output here, so let's say output 1. And in the next circuit, we do the exact opposite. We ground the positive terminal, and we only give voltage to input voltage to the negative terminal, and we will come out with V out 2. And my net V out will be nothing but V out 1 plus V out 2, which is exactly is the definition of superposition. So let's analyze both these circuits step by step. So we remember the op-amp properties. Op-amp properties that whatever is happening on this terminal, whatever voltage is happening here at this point, the same thing will happen on the positive terminal. So once that is clear, then everything is all right. So now let's see this part of the circuit carefully, this part, and it can be redrawn. It's just a voltage divider circuit. So in a voltage divider circuit, what's happening here, that we have a voltage V out, which is here. It is traveling back and getting grounded. So this whole, and we know that no voltage enters the negative terminal of the, no current enters the negative terminal of the op-amp. So this whole circuit then translates into this V out getting divided over 2 resistor networks, and then in the center point, this voltage is going to the negative terminal of the op-amp. So what is this V negative? V negative is nothing but voltage across this resistor. And what is that voltage? This is nothing but a voltage divider, so R1 plus R2, and whatever is the voltage coming from top, which is V out, which this is exactly what I've shown here. And if you solve this, V negative is nothing but V out by 2, because both these resistors are equal value. So now we know what is the voltage at this point. Once we know what is the voltage at this point, exactly the same voltage will appear at this point. So let's see what's happening there. Now this circuit is also acting, this whole circuit, the voltage is applied here, and the current is going towards the ground. So this also is acting as a voltage divider, and this whole circuit can be written like this. So V in is coming from top here and passing through the resistor, and through the capacitor it's getting grounded. So whatever is the voltage here, it is entering the positive terminal of the op-amp. So this again is a voltage divider circuit, so it can still be written as, basically we are checking the voltage across this capacitor, which is nothing but capacitor has reactance, so R2 plus XC. This is what is this voltage divider doing. Then whatever is the voltage coming from top, which is V in. So this is what I have written here. And then reactance of capacitance is nothing but 1 by JWC, where W is 2 pi frequency of the signal and C is the capacitance. So I've just substituted this XC here, and we get this expression here. And when we further simplify it, we land up with this particular function. So now we know what is the voltage at V plus. Earlier we had figured out what was the voltage at V minus, and we know that in op-amp V minus will always be equal to V plus. So we'll use that property and equate both these equations. So my V negative terminal was V out divided by 2, and my V plus was as shown on the screen. And then we solve this equation. We basically bring V in this side and take 2 on the other side, and this becomes my equation number 1. So this particular circuit is analyzed. Let's go to the other circuit. Now here, unlike the previous circuit where this was grounded and input was applied here, we are doing exact opposite now. We are doing grounding here, and we are supplying V in here as shown in the circuit, and this will generate V out. So let's analyze this circuit. Let's start with the positive terminal. Firstly, it is grounded So even if there was some residual charge on the capacitor, it would have got grounded through this ground. And this resistor is also grounded, which means there is no voltage here. V plus will be 0. If V plus is 0, then exactly the same thing must be happening here. V minus should also be 0. Now for this to happen here, what will happen? This is again acting like a voltage divider circuit, which is shown here. So this is V out 2, and through R1 and R1, this is the configuration that we have. Now for this terminal, V minus to have 0 voltage, exact opposite voltage should be at this terminal. That means at Vn, which means V out is nothing but exact negative of V out. Then only here 0 voltage will appear. So pretty straightforward. And when we rearrange this equation, we get V out by Vn is equal to -1. That's a pretty simple analysis. Here nothing is happening because everything is grounded. So no voltage is entering there. So that's fine. Now we have found out this is V out 2. Now we will use the principle of superposition and do this. V out 1 by V in plus V out 2 by V in is nothing but total V out by V in, which is nothing but the transfer function of the op-amp circuit, the net op-amp circuit. So this is what I'm doing. So I am going to add these two. So from the first circuit we got this term, and from the second circuit we got this. When this denominator goes here, and when we solve this equation, we get this expression. This is exactly what we started out to look for. Now if you look at the magnitude of this function, it is nothing but 1 square, basically real component, imaginary component, squares of that. And similarly for the one for the denominator, so both these magnitudes are equal, they will cancel out, and hence we will always get one constant one, irrespective of what the frequency here is. What the frequency here is. So this is acting like an all-pass filter. What about phase? So we know this is the imaginary part. So my imaginary part divided by real part, tan inverse of it, and this term is in denominator, so minus sign here, and then imaginary part divided by real part. Now we know that tan negative is also equal to minus tan inverse. So we have used that property and then added both of them together. So we get minus 2t tan inverse WR2C. So here you can see clearly that the angle, that the phase is dependent on frequency. And how is it dependent? Let's see. So let's see what's happened when W is equal to R2C, which means 2 pi f is equal to 1 by R2C, which means frequency is equal to 2 pi R2C. When that happens, this whole expression becomes this. Omega R2C is nothing but 1 by R2C into R2C. This cancels out. So now this whole expression becomes 1. And when that 1 becomes, we know that tan inverse 1 is nothing. This happens at 45 degree. And since 2 is multiplied with it, so this will happen at minus 90 degree. Right. So we have found out a frequency where the phase changes to minus 90 degree. And what is that frequency? This is that frequency. 1 by 2 pi R2C. At this frequency, the phase becomes minus 90 degree. Now if we keep increasing this omega, so omega and phase shift in degree. So if omega is 0 radians per second, phase shift is 0, and as it keeps increasing, at frequency 1 by 2 pi RC, this phase shift becomes minus 90 degree. As it keeps increasing further, at some point it becomes a total minus 80 degree and it stops. So that's how we are getting that phase that we saw in the Python script. And now we are 100% sure that this circuit acts like a phase shifter, acts like a all-pass filter. So from theory to a fully functional electronic circuit. In the next section, we'll implement